Hey everyone, welcome back to The Learning Addict. Today we're tackling a common headache in Go development. We've all been there. A Go routine hangs, a mutex deadlocks, and suddenly your service is a zombie. It's technically running, but it's not doing any actual work. Today we're solving that problem using the systemd watchdog. The concept is simple. Your app sends a constant I'm okay heartbeat to the OS. The second that signal stops, systemd pulls the plug and restarts the process automatically. It's one of the easiest ways to add a layer of self-healing resilience to your Go applications, and I'm going to show you exactly how to implement it. So let's get into it. All right, let's jump right into the code. We're going to skip the noise and focus on the real engine of this project, the Watchdog integration. To get our Go program talking to systemd, we're leaning on the go-systemd library. You can see that here on line 7. Think of this as our translator. It allows our app to speak systemd's native language, specifically the notify protocol. This is the exact same system level protocol that Linux relies on internally to keep tabs on its most critical services. By using this package, we can bridge that gap perfectly. It gives us a direct line to tell systemd exactly when our service is fully booted, and more importantly, it handles those periodic heartbeats that keep the watchdog happy. With our imports in place, let's move on to the main function. On line 10, you'll see a variable named work count. We're actually going to see that in action a little later, so for now, let's just skip this and focus on the main flow. All right, the very first thing that the main function does is send a ready signal here on line 16. What this does is send a notification back to systemd that the service has finished starting. Under the hood, this sends the message ready equals 1 to the systemd notification socket. And if I hover over here, you can see the string ready equals 1. If your service is configured with type equals notify in your service file, systemd will actually wait for the signal before it considers your service fully started. So this is the line essentially telling the OS startup is complete and the service is ready to operate. You also notice that the first parameter is set to false. That simply means we aren't removing the notify socket environment variable after sending the notification. We're keeping it around because we're going to need that connection open to send our heartbeats later on. Next, we create a ticker. A ticker is basically a repeating timer. In this case, we're telling Go to generate an event every 30 seconds. Think of it as a metronome that ticks at a fixed interval. Right after that, we call defer ticker stop. This ensures that if the program ever exits, the ticker is stopped cleanly so that the internal timer resources are released. Next, we enter the infinite loop. All right, inside that loop, the first thing we do is call perform work on line 23. This represents whatever the service is actually supposed to do. Maybe it's checking device status, maybe it's processing tasks, maybe it's even pulling hardware. In our example, the perform work function simulates this work while also allowing us to demonstrate what would happen if the service ever hangs. Here's how it works. So in the first 2 cycles, we simulate normal work within the watchdog interval. On the 3rd cycle, it simulates a hang, sleeping longer than the watchdog timeout. Now remember that word count variable I asked you to ignore at the beginning? This is exactly why it exists. This one here. The global work count keeps track of how many times perform work has run, which allows a function to behave differently on each cycle. This gives us a predictable way to illustrate normal operation versus a simulated failure, all in one program. Now let's return to the main loop. Once the work finishes, we send a heartbeat to systemd, and we do that on line 25. This line here sends the message watchdog equals 1 to systemd. I can prove that by hovering over this, and you see here watchdog equals 1. If this heartbeat doesn't arrive within the expected time, systemd assumes the service has stalled or crashed and can automatically restart it. And again, the first false argument means we keep the notify socket environment variable around so we can keep sending notifications. And finally, we hit this line here on line 28, which is less than sign dash ticker.c. This is where the timing happens. Ticker.c is a channel that receives a value every time the ticker fires. By reading from that channel on line 28, the program pauses until the next tick arrives. Since we configured the ticker for 30 seconds, that means this loop waits 30 seconds before starting the next cycle. So the flow becomes very predictable. The service performs its work. It sends the watchdog heartbeat to system D. It waits 30 seconds and then repeats the process again. This structure ensures that system D always gets heartbeats on time, unless something goes wrong, in which case the watchdog will step in. Now that the Go code is ready, we need to look at the other half of the equation, the system D service configuration file, which is this service file right here. So in this file, there's 3 key directives that make this work. First one being on line 5, which is type equals notify. This tells system D to stay in a starting state until it receives that ready equals 1 signal we wrote earlier. Next one I'm going to talk about is Watchdog seconds, which is equal to 30. This is our deadline. It tells system D if you don't hear from this app every 30 seconds, assume it's deadlocked and take action. The next one's right above it. Restart equals on-failure. This is the autopilot switch. If the watchdog timer expires or the process crashes, system D will immediately spin up a fresh instance. In our code, our loop runs every 30 seconds, but the work itself only takes 15 seconds. That gives us a comfortable window to send the heartbeat in on time. But if that go routine ever hangs before it can send watchdog equals 1, system D pulls the trigger and your service is back online automatically. This handshake between your Go code and the Linux init system is what keeps your applications healthy without you ever having to log in and restart things manually. All right, enough talk. Let's see this actually work in a live environment. First, we need to get our service into position. I've placed my compiled Go binary in /root. So I can do that, do an ls there, and you can see my binary is there. And I moved my service file into /etc systemd system. And you can see that here in Go Watchdog Service. One thing to note here is if you placed your binary in a different location, you will want to edit your service configuration file. /go. Okay, and you will want to do that here. Change this to the path of where your binary exists. Okay, I'll exit that. Now that we have everything in place, we just need to tell systemd to recognize the new configuration and kick things off. And we can do that by running system control daemon reload, and then system control start Go Watchdog service. All right, with the service live, let's watch the logs. We can do that using journal control here. All right, so here we see that it sent the ready signal. So it's doing work, and we just sent our first watchdog equals 1 heartbeat. Okay, and then on this third cycle, if you remember from the code, it should trigger a simulated hang. Watch the logs right as we hit that 30-second mark. And there it is. Systemd detected the silence, realized the service was a zombie, and pulled the trigger. It sent a kill signal and immediately spun up a fresh instance. Now we're back online with a fresh process ID and processing work again. If you're running Go services in production under systemd, adding this is one of the quickest wins you can get for your infrastructure. It transforms a basic service into a self-healing one that can recover from deadlocks and hangs without you ever having to lift a finger. Thanks for watching The Learning Addict. If this helped you out, let me know in the comments and I'll see you in the next video.